let's discuss a little bit about the early chemical history. Chemistry has been around us since people have been around, ever since people have looked around them and wondered what it was that made up their surroundings, themselves, the universe. The Greeks were the first to try and explain chemical changes. So in about 400 BC, we have a man named Democritus. And Democritus dealt with science in a very, very primitive way. He was more of a philosopher than an actual scientist. And he said that matter is composed of small, indivisible particles. And he named those individual particles atomos, which is the beginnings of the name atom. However, like Democritus and all Greek scientists of that time, they didn't do any experiments to test their ideas. So we're going to zoom up pretty fast, up about 2,000 years or so. Real quick, early on in chemistry, people believed that there were 4 essential elements: fire, air, water, and earth. And then we had scientists which were called alchemists. And alchemists did a lot with metals, and particularly changing metals into gold. And some were mystics and fakes, but some were actually chemists who discovered several of the elements. Now we're moving up to the 1600s, and we want to talk a little bit about a man named Robert Boyle, and he'll come up several times throughout our year in studying chemistry. He was the first chemist to perform quantitative experiments. And when we think about quantitative experiments, again, we remember that those are experiments that require measurements and measuring devices. And in particular, Robert Boyle dealt a lot with gases and the relationship between pressure and volume. And he also found that substances could not be broken down any simpler, were called elements. Joseph Priestley, 100 or so years later, was also a chemist who worked primarily with gases. And one of the things that he's known for is discovering oxygen gas and the need for oxygen gas in combustion reactions. So we move up to the late 1700s, and now we talk a little bit about Lavoisier. And Lavoisier explained the true nature of combustion. And he was a very quantitative chemist, which meant that he made a lot of measurements involving combustion reactions. And what he found was that mass is conserved during chemical reactions. And he verified this thought called conservation of mass. Mass is neither created or destroyed during chemical reactions. We move up to the early 1800s, and we have Joseph Proust. And Joseph Proust dealt with the proportions by which different elements were found in compounds. And he said that a given compound always contains exactly the same proportion of elements by weight. And this is known as the law of definite proportions. So as an example, if we were to look at the compound copper carbonate, it contains copper, carbon, and oxygen atoms. And when we compare these elements by weight in the compound, copper is 5.3, carbon is 1, and oxygen is 4 by mass ratio in that compound. John Dalton did a lot for science, and he reasoned that not only do compounds contain the same proportion of elements by weight, but they also contain the same number of atoms. So one example he carried out, one experiment, contained carbon and oxygen. And what he did was he compared the weight of oxygen with 1 gram of carbon. And he found that there were 2 different compounds that formed between carbon and oxygen. In the first compound, for every 1 gram of carbon, there was 1.33 grams of oxygen. And in the second compound, for every 1 gram of carbon, there was 2.66 grams of oxygen. And when we look at those numbers, 1.33 and 2.66, what do we notice about them? The second is twice the first. So compound 2 has twice as much oxygen by mass as carbon. And this is called the law of multiple proportions. When 2 elements form a series of compounds, the ratio of the masses of the second element that combine with 1 gram of the first element can always be reduced to a small whole number. So going back to Dalton's experiment, if we were to look at 1 gram of copper combining with oxygen, it combines with 1.33 or 2.66 grams of oxygen for every 1 gram of carbon, which is a simple, small, whole number ratio. Twice as much oxygen in the second compound as the first compound. Another thing Dalton came up with is what's called Dalton's atomic theory, and there are 4 statements in Dalton's atomic theory. The first statement is that each element is made up of tiny particles which are called atoms. The second part is that atoms of a given element are identical. The atoms of different elements are different. Now, we didn't know exactly what it was about atoms of the same element that made them the same, and atoms of different elements that made them different, but he knew that there was some fundamental way in which this occurred. So atoms of the element sodium are all the same. Atoms of the element chlorine are all the same. Atoms of the element sodium are different than atoms of the element chlorine. But again, he didn't know exactly how they were different. He just knew that they were different. The third statement deals with chemical compounds. And chemical compounds are formed when atoms combine with each other. And a given compound always has the same number and type of atoms. Like if we were to look at the compound sodium chloride, it's the chemical combination of 1 sodium atom for 1 chlorine atom. Or if we were to look at water, we have hydrogen and oxygen chemically combined together, and the ratio is 2 hydrogen atoms for every 1 oxygen atom. The fourth statement in Dalton's atomic theory deals with chemical reactions. It says that chemical reactions involve the reorganization of atoms, changes in the way they're bonded, but the atoms themselves don't change. So in other words, when we look at chemical reactions, all we're doing is taking the atoms that are in a particular arrangement and rearranging them. So Dalton's theory deals with atoms, how atoms combine together to make compounds, and how compounds react together in chemical reactions. Joseph Gay-Lussac is another scientist that we should be aware of. And he dealt with gases, and particularly he dealt with how temperature and pressure are related. And these were experiments that were keys to showing the formulas for compounds. So one of the things that he did was he compared the volumes of reacting gases with their products. And he found that there were specific ratios. For every 2 volumes of hydrogen that combined with 1 volume of oxygen, it formed 2 volumes of gaseous water. And he also noticed that for every 1 volume of hydrogen that combined with 1 volume of chlorine formed 2 volumes of hydrogen chloride. Avogadro is another person that we'll be dealing with throughout the year. And he's a scientist who dealt with how temperature and pressure are related, but he went a little bit further. He discovered that not only do equal volumes react together, but equal volumes of gases contain the same number of particles. And this is called Avogadro's hypothesis. And another thing that Avogadro is known for is what's called diatomics. There are some gases that will always be found in diatomic form. And when we look at that, di means 2. So diatomic means we're looking at molecules that are made up of 2 atoms of the same element. Oxygen is an example. If we have oxygen gas, it's O2. Or nitrogen is an example, and that's N2. And a way that we can remember diatomics is they are what we're going to refer to as Hunkelbriefs. Hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine are referred to as Hunkelbrief molecules because they're diatomic. Hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. They will always be found in diatomic form.